Okay, this is the second session of the series of course about probability logic of high-king arithmetic. And well, in last session we just have seen the axiomatization for what is meant to serve as the probability logic of high-king arithmetic. And this session we will explore more and try to figure out which kind of semantics best suits for this logic that we introduced. Before we go for semantics, we first well recall some notions, namely first by translation, the box translation. We annotated as a box. Uh, well, it is well aligned with the BHK Kolmogorov Brouwer-Hating Kolmogorov interpretation of the validity of formula in the intuitionistic setting. This translation, if you interpret box as the proof predicate, that's why it shows up very naturally in the study when you study probability predicates in the intuitionistic level. So it is defined recursively. The idea is that you put box behind any subformulas of this formula A. So it is exactly as being expressed in the BHK interpretation. So, for instance, you define B and C box as uh, B box and C box because, well, you don't need to put any boxes behind B and C at this point. You could do that, but it is not necessary, and we do in a minimal way actually. B or C in the same way. So it is defined as you see here. The important case is the implication. B arrow C box is defined as B box arrow C box. Well, the box dot of this formula, the box dot means that the formula conjunction with its box, right? And for the atomics, it's treats the atomic formulas separately. It depends that if it is well for the box formula, it is defined as it is because it already implies by sigma 1 completeness we have its and the box translation doesn't go through the box formulas as well. It is another point here to notice. And well, then we have to define for atomic variables. It is defined as the box dot of the atomic variables. Uh, for the uh, for the simplicity of some notations, later to gather both sigma 1 substitutions and arbitrary substitutions, we augment our language to include two sorts of atomic formulas. One sort is variable, another is parameter, but it is not necessary in the axiomatization of the probability logic of high-king arithmetic. You can consider that the set of parameters at the end is an empty set. It is only serving for the intermediate levels for the reduction purpose. So for parameters are annotated as PQR and variables X, Y, Z. So P box is just P because P is meant to replace by sigma 1 formulas, and by sigma 1 completeness again we have the intended interpretation that we have in our mind. And well, this is the box translation. But the main point is that most of our intuitionistic model logics like IGL are closed under this box translation. Namely, when IGL implies A, then IGL implies what A box, at least for nil formulas. When A is a nil formula, then we have this closure condition. And well, this is one thing that I wanted to say. It will show up naturally when we want to provide the Kripke model, the probability models for the system IGLH that we introduced, the candidate for the probability logic of high-king arithmetic. This operator, this translation is showing up naturally. Another thing is the set of well, the notion of projectivity. projective formulas are more important and more handful tools in the literature. They have been introduced by Silvio Ghilardi first, and he used these projective formulas as a basic tool for the characterization of admissible rules of intuitionistic logic first, and then for the characterization of admissible rules for modal logic. Actually, Emil Yerjabek used this tool actually. Well, let me first give you what is it. What it is. Well, given a formula A and the logic, A is the substitution theta is called A projective. Uh, if it satisfies this property that for any variable x, we have in the logic L, the formula A implies theta x is equivalent to x itself. So this is what it is called a projective substitution, a projective. So in a sense, it says that the substitution theta is identity substitution in the viewpoint of the logic L together with the axiom of the formula A, right? It is called a projectivity. The projective formulas are about if on top of this condition, theta also unifies A, theta is a unifier of A in the logic, then theta would become the most general unifier of A. You can argue very easily. That's why projective formulas are very important. But at this point, I don't require the condition of being unifier of A. So theta just say that theta is an A projection. Um, well, the the generalization that I consider in this work for the characterization of probability logic is to just consider relative projectivity. Well, in projectivity that's introduced by Silvio Ghilardi, uh, theta must unify A, as I told you. So A is called projective if there is some A projection theta which unifies A. So A is projective, so it is the definition of projectivity. A is projective if there is some uh, A projection theta such that uh, uh, unified unified thing. So if there is a projection which unifies the formula, then we call that formula as a projective formula. And this formula possesses a most general unifier due to the existence of such uh, nice object. Every other unifier of this formula would become a less general formula, a less general substitution, in the sense that that substitution, if composed with the theta itself, would become the substitution that is given, namely if lambda is a unifier of A, then you can say that lambda is equivalent to uh, lambda or theta. This means that any unifier of the formula A is a less general unifier than theta itself, because you're composing this with theta and you arrive at lambda. So you already had a more general unifier before. So no new unifier would be introduced as soon as you have a projective unifier. Why? Because, well, if A is being unified by lambda and it is satisfying this property, then you can take by the closure under substitution, you can take the lambda substitution on this equation, then lambda A becomes a valid theorem and lambda O theta becomes equivalent to lambda, which means that lambda is less general than theta. So that's why projective formulas are very important. and they serve as a very building block for the characterization of admissible rules of intuitionistic logic. But the notion that we need here is a bit more generalized form of this. We call it relative unification, the work that I explored more with Constantinus later. And well, it is we found some nice connections, but at this point I only keep stick with what we actually will be needing for our purpose. What is the relative projectivity? Okay. For a given subset of box formula, we are going to treat box formula as parameters. Parameters are not being substituted with any substitution. So substitutions theta that I talked about here would not replace parameters, just replace variables. We have these two sorts of parameters and variables. And Marx formulas also are going to be treated in the model language as parameters. So the substitution doesn't go inside the box formula. This is just for technical purposes that we will need later. So just to distinguish the usual substitution with these kind of substitutions which does not touch inside the boxes, we annotate these new substitutions as the hat of the substitution, theta hat. It annotates the restricted form of substitution, which replaces uh, atomic variables which are outside the scope of the modal connectives by as it is defined by theta, and the variables which are appearing inside the modal operator would not be changed. Okay, having all these in your mind, then I can define the gamma projective formulas instead of. Well, when you come in this modal language, you cannot expect that formula would be unified in the sense that all the parameters and but if you consider this kind of extension, you cannot expect that parameters and modal operators would be annihilated and unified. At least parameters would remain unchanged. So you need to consider kind of a relativized version of this notion of projectivity. Namely, we define as gamma projective for a given set of formulas, which usually would be a set of nil formulas. But at this point, let's define in general, not to get involved with the details of what gamma is. A gamma projective formula. So A is gamma projective. It is the definition. Uh, A is gamma projective if firstly if there is some A projection such that uh, up to now it is exactly what we define as projectivity. So there should exist some A projective substitution theta such that instead of saying that theta unifies A, we say that the theta of A belongs to gamma. Okay? So uh, theta of A, the theta hat of A actually, would belong to gamma in terms of one logic and equivalency in some logic that we are studying. This is the notion of gamma projectivity that we are going to consider. So for given a set, the set of all gamma projective formulas are annotated as down arrow gamma, right? So down arrow gamma is the set of all gamma projective formulas. This is some notation that I'm going to use later. And specifically, we are interested in gamma, which is actually nil, but not exactly nil. At some point, nil. At some point, it is some even subset of nil, namely a nil box. The Boolean combination, the nil combinations of the formulas which are in nil, but there is no atomics outside boxes. Let me explain these two classes of formulas also. Okay. We uh, let us remind about these two notions. Firstly, nil. Remember what was the nil? Nil is the class of the set of all formulas with no nested implications to the left. So if a formula does not have any implication to the left, actually, as much as it is outside the scope of modal operators, you should treat modal operators as atomics in this setting. So a nil formula in the modal language would be treated in this way, that each box formula with all complexity that it might have could be considered as an atomic. And well, the nil formula in this setting would be just a nil formula as we had in the intuitionistic setting of non-modal language with this additional um, convention. And this is one class that we are considering. Another class is the box dot well, the S nil. We annotate it as Sn. What is S nil? Is exactly the class of uh, formulas in nil such that this formula is equal to the box translation of some formula. So I would say there exists some B such that A equals to V box. So the S nil is kind of strongly nil formula in this sense that they are self-complete with this translation that we had here. Okay. This is one class of formulas which we are very much interested in relative projective unification class, namely bound arrow S nil is one of the classes that we consider here. Another class is the S nil or SNB, S uh, nil box. What is this? It is just what exists in Sn, but without any atomics outside of the boxes. So instead of A is in Sn, such that A does not have any atomics outside boxes, right? Okay, these two classes and their down arrows. Well, actually, the down arrow for this is what we interpret for our uh, later applications. Okay, so what are the connections of these kind of weird classes of formulas to the axiomatization of probability logic? The connection comes through the admissible rules. Maybe just to better understand the motivations, I would do some digression here to explain that what is the connection between projective formulas, the standard projective formulas and admissible rules of intuitionistic logic, and the system that I introduced last session, which would be which meant to be serving as as an axiomatization of proof logic of Heiting arithmetic. It would be very helpful. Let me do this. So okay, and now let us get back to the axiomatization of the system that I introduced. I defined last session, namely AR, and define it as follows. If A arrow B is a theorem of the intuitionistic logic, then we say that it is an axiomatization for a binary relation. It is just a binary relation between formulas of the model language or propositional non-model language as we need it, as we change between the languages as as we need it. So it is an axiom of theorems of this logic. And let's start with the version which would be serving as the system for the probability logic of Python arithmetic, and then varies it as we need. The second axiom is saying that A, B, the cut through, B, C, AC, the conjunction rule, A, B, and A, C, A, B, and C, the disjunction rule, B, C, and A, C, A, or B, C. One rule that I missed last session, I noticed from my notes actually. I think I haven't written, but maybe if one of you have written some notes, is this axiom actually? The Lehman axiom, I called it in the paper. It is saying that A infers what A? The Montañez axiom, it says that if A uh, B then a triangle B then box E, well, I write this way. Then E arrow A, E arrow B for E in what formulas? I would write it this way. So it is just formulas which are assumed to be sigma 1. E can only be sigma 1 in this rule, which in our probability interpretation, it means that E could be either boxed formula or parameter if you extend it with the set of parameters. And the Fisher axiom, which says that B arrow C triangle, the disjunction of EI conditionally refers, oh, sorry, I from 1 to n plus m, such that B is the conjunction of EI's arrow FI's I from 1 to n, and C is disjunction of I from n plus 1 to n plus n. This is Visser axiom, and that is the full axiomatization of the system that we call AR1. Well, in previous session I annotated it as AR, but it doesn't matter because this session I need to have three versions of this system. I have subscripted AR1, and the proof of the logic of Python arithmetic would be IGLH. What is IGLH? Is IGL plus the set of box A arrow box B such that A triangle B is derivable in AR. Okay, this is what we want to prove, that it is proof of the logic of Python arithmetic, but the process would be including to reduce this probability logic to the sigma 1 probability logic of Python arithmetic. So before going one step forward, let us also introduce the system that is already proved to be the sigma 1 probability logic of Python arithmetic. But what is the sigma 1 probability logic of Python arithmetic? The sigma 1 probability is just uh, defined as we had for the definition of the probability logic. But for the substitutions that are being considered, you should restrict the substitutions only for sigma 1 sentences instead of arbitrary sentences. So you only have sigma 1 sentences being replaced for uh, for uh, for atomic variables and atomic parameters as well for the language of for the propositional language. And well, the resulted system would be the sigma 1 probability logic of Heidegger arithmetic. In classical case, the sigma 1 probability logic of piano arithmetic and classical mathematics is first studied by Albert Fisser himself, and he showed that the system GL plus the completeness for atomics, this axiom, which we call it CA, completeness for atomics. By atomics, I mean atomic variables, not atomic parameters. By completeness for all atomics, this case, it will be better to write it as A for both atomic variables and parameters. If you add this additional axiom scheme with, to GL, the result would not be actually a logic because it wouldn't be closed under substitutions anymore, but it would be arithmetically complete for the sigma 1 substitutions. It is arithmetically sound because A is meant to be a sigma 1. By sigma 1 completeness, we have the validity of this axiom, extra axiom scheme. And the completeness also more or less in the same way that the arithmetical completeness would be resulted, for this also would be resulted. A bit of uh, 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 revise in the proof is needed, but the Solovay proof also works for this. So in classical case, we have this actually after the characterization of the full probability logic of piano arithmetic. In Heidegger arithmetic, actually, we have the same IGL. Here we have the completeness for atomics. Uh, this system still remains as we have. Well, it's, yeah, better to write it as H1. And H sigma, it is just IGO C plus box A implies box B such that AR sigma impairs A triangle B. What is AR sigma? AR sigma is exactly. I will change and optimize this system to arrive at AR sigma. I will write chains in other colors such that it will be noticed what is the difference. Here, the CA axiom would be added. So if IGL CA implies an implication, then you have the triangle of those formulas. The rest here in this line would remain unchanged. This also remain unchanged. But this box formula, it uh, would be atomic or box. So I will write it A box. A box means that it is either atomic or box. Any kind of atomics, parameters, or variables are accepted. And also boxed formulas are also accepted. So if E belongs to atomics or box formula, so it can be parameter variable or a box formula, and you still have Montagnais. No, exactly. You should adapt this system in a way that the sets of formulas which were assumed to be sigma 1 should be changed to also include variables. This is the only thing you need to do. It is, in short, if I want to express what is how you need to change this system to arrive at HR sigma as being needed in the characterization of sigma on true the logic of Heidegger arithmetic, you need to do this change. And here also I would add uh, this atomics as well. So if in the consequent you also have some atomic formula, you just consider, well, it is, remember that it is a conditional implication in which if the consequent belongs to this set, then it would be the consequent itself without antecedent. And if it does not belong, then the implication would be as usual, standard implication. So it is uh, kind of conditional implication in which the condition would be changed to include atomic variables as well. And that's the only change, but it is a major change. This system, AR sigma, is way more uh, better behaving system, as we will describe later. It can be described very easier. The complexity of this system is considerably lower, and it is serving the sigma 1 probability logic of Heidegger arithmetic. And that's why the characterization, the arithmetical completeness of sigma 1 probability logic appeared first, and it was easier because we could treat the system by a very simple simple observation that how this system actually works. If you remember from the previous session, we showed that Fisher algorithm, uh, based on these rules of inference, excluding some of them, provided the nil algorithm. Namely, by these set of rules, one could provide the best nil approximation from below, right? And actually, that's the point about how we can characterize this system. So, what is the observation? I will write it in the other hand side. The observation here is that um, this system actually maximizes the nil preservativity relation. What is the preservativity relation? The preservativity relation for a logic or theory T and a set of formula gamma is defined as for any formula in gamma, if P implies E arrow A, then P implies E arrow B. This is it is called gamma preservativity logic of the logic T. And no, this system actually axiomatizes the nil preservativity of ideal CA. So let me write it as a theorem. It is the theorem that I'm not going to prove, just state it as it is. So it says that AR sigma implies A triangle B if and only if I, D, L, C, A, and nil. Oh, S nil, not nil actually. You remember what is the S nil? The class of nil formulas, which are also the target of the box translation as well. A Sn preserves B. This is this is the theorem that shows that actually by this system you can show that uh, the nil S nil preservativity is exactly what it axiomatizes. We will see that why this theorem becomes important. In comparison to this theorem, we also have another characterization for the system AR1. I wrote first. It is the second theorem that I'm going to use today. AR1 implies A triangle B if and only if. Here, actually, the projectivity shows up. If and only if A in ideal preserves B with respect to the set of part dot of projective to Sn. So uh, it is, what is this set? Let us forget about box dot. It is the set of formulas which are projective to a formula. Oh, better some update. Well, let me again. What is this class? First, Sn box is the class of formulas which includes nil formulas made up of only boxed formula or parameters. And it should also be in the target of that box translation. And here we have the set of formulas which are projective to one of those formulas. And here we just put a box dot behind all those formulas. So their conjunction with their boxes would be considered and gathered to a set of formulas. And it is exactly axiomatized by this. Projective, it is a relative projective. By I define here actually.
Remember, yeah, but what does it mean? What does it say? Some class gamma is projective to class gamma. Formula A is projective to class gamma.
Well, again, here we have a class of formulas, and you can talk about the formulas which could be projected to a formula in this set. And this is okay, what is the meaning? It is exactly what I defined. It is just to remind you. Let me define what is this. It says that a formula belongs to here. A belongs to here. We can only if there exists some substitution theta. Okay. There exists some substitution theta such that the firstly, well, we should set up that in which logic we are talking, but in this setting we are talking about the logic would be ideal. I just skipped these details. But in IGL we should have firstly that the theta hat of A belongs to gamma, and in IGL again A should imply that the theta of any variable would be equivalent to the variable itself, or any variable itself.
What's theta hat? What
Theta hat is the substitution in which does not goes inside the modal operator. Namely, the theta hat is defined recursively for a variable is as theta, for parameters and variables, for conjunction, disjunction, implication of booleans are as theta, and for box formulas it is identity. It doesn't go inside boxes, right? So it really and literally treats box formulas as parameters, exactly in the same ways that parameters are not being replaced in the substitution by a substitution by default. Box formulas also, in terms of theta hat, does not being replaced by.
But then it's really strange. It's because it's asymmetrical, right? Because you have theta hat to the left.
Indeed.
This without hat on the right, this is very kind of strange.
Yes, this is a bit strange, but given that we are in IGL and we have the fixed point lemma, this kind of non-symmetry phenomena could be mended by the effect of the simultaneous fixed point. In the end, that we actually need to use this kind of substitution later. So by fixed point lemma, you can just make sure that these substitutions actually are not changing in terms of the logic that you are studying, actually in IGL, because you are working in IGL. You can make sure that this kind of change that you expect would be could be met by fixed point, by uniform fixed point lemma.
Okay, yes, so to say what basically you somehow can hear the application. For example, you will be able to match simply with theta hat to make a theta and theta hat identical.
No, I'm not telling this.
Okay, you take something else.
Yeah, I'm telling that in well, the non-symmetry that you're talking about is some concern that would cause some kind of disaster at some point that you actually need to use it. But at that point, the fixed point lemma would save it. That's what I'm telling. I'm not telling that theta and theta hat would be coincided, but you can actually mend this non-symmetry effect. But let us forget about this at this point because it really doesn't matter at this point.
Okay.
And well, Okay. Okay. Mhm. Uh, I will explain exactly today. Today is the day that I am using. I'm telling everything that I am going to use. So if we wait for some minutes, I will arrive. Let me first define the probability models, and then we arrive at this. Then, actually, just to shortly answer this question, is to provide semantical completeness. We show we introduced some probability models for these systems, mainly IGL H1 and IGL CA H sigma. These two systems are going to be sound and complete for some kind of probability models. And for the soundness and completeness, specifically for the completeness part, we need completeness of this system for probability models. We need this characterization. So this characterization is really handful there and only there, right? Okay. So let us continue with the probability models. Now I will talk about probability models. The problem of this system, IGLH, is that they are not well behaved for standard crypto models because the frame properties are getting super complicated to become decidable and handful tools for the study of arithmetical completeness and reduction purposes. These kind of crypto models have been studied by Rosalie Imhoff in her PhD, but as I tried out, I couldn't use them, and I needed to invent some new kind of semantics which have finite model property and better behaving. And this is the semantic that I am going to introduce. And well, later in a collaboration with Borge, actually Borge Sierra Miranda, I well, we together tried out to see that how this kind of new semantics would work with classical model logics. In the case of GL, we don't have any surprising new result, but I would say for interpretability logics, we noticed that we have some kind of new viewpoint about the interpretability logic of piano arithmetic, namely ILM. And for instance, for GLP also we provided these kind of semantics. The kind well, we know that cryptic semantics are not sound at the same time and complete for GLP, but these kind of probability semantics becomes sound and complete. However, for the case of GLP, we couldn't provide decidability and recursiveness. It is just some kind of semantics in a similar manner as logical semantics are. It is trying to complete for GL, for instance, for GLP. Let me describe what it is here. But it was useful at least here for the characterization of the probability value. And let me describe. Here is the definition. Firstly, let me start with the cryptic models of intuitionistic model logics with a single unary model operator. A cryptic model for the intuitionistic model logic is including a set of words, an accessibility relation for intuitionistic arrow, another accessibility relation for the model operator, and uh, an evaluation B, right? It is a usual cryptic model for intuitionistic model logic. Box is defined, the validity of box is defined through this relation, and the validity of implication is defined through this relation, and the combination would become a cryptic model. One can show that, for instance, IGL, it is easy by canonical model construction. IGL is sound and complete for these kind of converse well-founded transitive. By transitivity, I mean that this relation is transitive. This relation is reflexive and transitive as default for the intuitionistic always. If this relation would become transitive, converse well-founded, then this model become sound and complete. Well, this IGL would become sound and complete for finite such cryptic models. And what is the probability model? The probability model is just a model with bunch of theories. So we have a standard crypto model of intuitionistic uh, model logic together with bunch of theories. We decide assigned to the set of words, and how we define the validity of formulas. The validity of formulas are defined through the theories, and it is very well aligned with the intended meaning of the probability predicate. Because we are talking about bugs as treating bugs as probability predicate, it is very natural to expect that in the cryptic semantics also bugs interpreted as probability in some theory, but the theory is propositional here. So it is defined. Boolean connectives are the validity of Boolean connectives are defined as we had in the standard crypto model. But for this crypto model, of some word, we define the validity of box A by definition as for any accessible node, we have T U implies A. Right? This is the definition of validity of box formula in the probability model. We require some basic facts about the theories that are being assigned to the nodes. Namely, this basic fact that TUs should include intuitionistic logic, but in the extended model language. Namely, all the axioms of intuitionistic logic should be included in TU. And also, we require that TU should be closed under model exponents. So we have these two conditions, basic conditions. So firstly, well, I would write them down as it includes intuitionistic logic in terms of this fact that firstly it should include all the axioms, and also it should include the model exponents rule as the rule of inference of that logic. So if this logic includes the formula and an implication as an antecedent of another implication, so the consequent also should be implied. And okay, this is the probability model. Let us see that how it serves for the aim of. Let me wipe this part. The first theory that I want to show you that it is sound and complete for is the IG of this sigma one probability logic of Heiting arithmetic. But before going for that, let me first show that how it interacts with the basic theories, logics actually that we are talking about, namely IGL and IGLC. For that, we need to require some extra condition, which we call it the fullness. For a set of formula gamma, we say that for a set of, it is another definition, for a fifth gamma of formula, P is called gamma pool if uh, gamma W is included with if PW implies gamma W. What is gamma W? Gamma W is defined as the set of all formulas in gamma such that uh, they are valid at the non-bubble. We say that this is the interaction between the standard Kripke model and the probability model actually. with this extra condition, we keep track of some trace of standard Kripke models in probability model, but not all. We don't need all the whole truths. We need some basic facts. And that's how we describe it via fullness, gamma fullness. The gamma usually in our settings would be either nil or S nil or S nil bar. So we consider two different fullnesses as we see here, as the soundness. Let me first soundness theorem that I can describe here is to say that ideal is sound for, well, I assume that all probability models are conversely well founded. So converse well foundedness is something that I consider by default. I don't say it again and again for the future soundness results. For probability models with uh, S, so IGL is sound for probability models with S nil box fullnesses. Well, I can describe how the soundness works, but the essence of this SN box here is just to provide the closure under necessitation. Well, all axioms are automatically getting value. Well, I still need some extra time. Oh, let me describe it. Having another look at the probability model, besides the frame properties that we usually have in the standard Kripke models, we have some kind of logical properties for the logics that are being assigned to the nodes. Namely, we could require that they are closed under some kind of rules of inferences, right? These conditions also could be expressed for these kind of probability models as well. So we have two different sorts of properties of probability models. One is as we had for the standard probability models. Another is for specifically for probability models, namely the rules of inferences for the logics for all of the logics that are being assigned to the nodes, not for one specific node. Okay, and that's the extra that gives the extra plus point to this probability model and makes it a better tool for some studies. Maybe you could replace some very tricky frame properties with some inference rules. This way, you can have a simpler viewpoint of probability models. That's exactly what probability model does in the simplification process. Actually, this is exactly how I personally advantage of this to have, for instance, a probability model for GLP, probability model for this probability logical arithmetic, and for ILM as well. For interpretive logic, classical Kripke models are having a bit annoying interactions between the relations, but they're actually with the joint work with Borfe, we could provide some kind of simplification. And here, as you will see, it will happen. So we can require that these theories are closed under some inference rule. Namely, uh, here actually for ideal, we need them to be closed under necessitation. Closed under necessitation. So ideal is sound for probability models which are SN box, S nil box full, and closed under necessitation. Sorry, what? No, that's why I am calling them theory, not a logic. Because indeed, indeed, exactly, exactly. That's one point that it's this these kind of substitutions very much aligned with these kind of semantics. As much as we are working with this, you're right. So box formulas are just in the setting of these logics are just a black box, a sigma one formula as a parameter. Okay, the soundness proof. Well, I would some parts of the soundness with induction and the set of axioms and rules of inferences. You can prove the soundness to have some feeling that how this kind of probability model works. I will give you some examples. For instance, the validity of this axiom. To see the validity of this axiom, namely the axiom K, to observe that this axiom is valid, you the only thing that you need is that these theories that are being assigned to the nodes are closed under modest points. Actually, the modest points rule of inference will be reflected as the K axiom, the validity of K axiom. This is one point that you can easily observe. So because PWs are closed under modest points, this axiom is valid at any node, any point, anywhere. And the other issue that probably one should face is to, because we have necessitation, we should be able to also show that the validity of the box of the K axiom should be valid. This is where S and box fullness would become handy. Actually, that's why we need fullness. Fullness is only required for the necessitation. Actually, the box of the K axiom to see its validity, we need that this axiom should belong to any nodes, should belong to any theory that exists above this node W. So let me write down. We see that it is P. Let us annotate it as phi. We want to show that y is holding in some node W. We need to, by definition, see that for any u accessible from W, we need to see that TU actually implies this K axiom phi. Okay, we don't have any clue to see that unless the gamma, the SN box fullness. These act all. If one looks at all the axioms that are listed in this set of axioms, one could observe that all axioms belong to SN box, and that's why exactly IGL is closed under box translation. By the way, SN box. Uh, and well, given that it belongs to a sandbox and it is valid at the node U by the same argument that I provided here because of the closure and the modest exponents, you could say that by a sandbox fullness, this phi should belong to TU as well. And well, this way you could. At the same time, we have seen that it is not only sound ideal. One extra thing that you could have on top is that all the logic, all the theories that are being assigned to the nodes are also by default should include ideal as well, right? So it is the soundness. The rest of the proof is quite more or less similar to this argument that I provided. For instance, the axiom 4, the transitivity axiom, is because of the closure under necessitation, uh, etc. So we have the soundness of IGL for these kind of proofs models. And similarly, let me wipe this out. Similarly, we can have. So we have one more soundness, namely IGL CA is also sound is sound For I would write CA probability model. By CA, I mean that if an atomic formula is valid at some point, it should be valid at any monally accessible nodes above that. So CA probability model. With this time, we need, instead of S and box, we need SN fullness. And again, closed under necessitation. Okay. This is the soundness and completeness of probability models for these basic um, systems, but we require that these logics are also closed under AR1 that I used in this system, AR1 and AR sigma. Then we have automatically the soundness of the logics that are candidates of the probability logic and sigma probability logic of Python arithmetic. So we can extend these results in this way that also we have ideal H1 is sound for these kind of models that appeared in this line with extra property that being closed under AR1. If they are closed under AR1, by closure under AR1, I mean that all the logics that are all the theories that are assigned to the node W's should be closed under these rules. If A triangle B belongs to AR1, then if A is a theorem of TU, then B also should be a theorem of TU. It is being required by force. So we require that these conditions should satisfy, and then ideal H1 becomes sound, and sound for these kind of the soundness part is very easy. And in a similar manner, one could say ideal sigma, ideal CA H sigma is also sound. Uh, Again, I should go here for models, for probability models as we described in the second line, together with the extra property by closure under AR sigma.
Go back. What I really don't understand about the definition of the model, but actually a connection between probability relations and assignment of theories. So, namely, my concern is that you course you want them to be in the end of the day, particularly models for Intuitionistic or and this is would require monotonicity of the relation. Right? But
Monotonicity in terms of
yes, but if you have something accessible via this kind of
intuitionistic.
Yeah, with basic
Yeah.
relations, obviously, yeah, then accessible world, anything that was valid in world will be also valid in accessible world.
For which models you are talking? These models of this kind?
Any no, I mean, I think
Oh, this kind. Yeah. Okay, a basic definition.
Pure, like I mean, this whole like builds like on top of
Right.
Okay, you don't understand why, how you guarantee this property.
These properties I didn't talk about. These are conditions that are already existing on the intuitionistic model, tricky models of intuitionistic model logic. Well, there are a bunch of these kind of requirements on the models here, which I didn't describe. I just skipped because they are already known in the literature, but I can just rephrase.
I'm not sure that everyone here is familiar with
Yeah, I can describe it. Well, there are several properties here for the crypto models of intuitionistic model logic. Namely, we require that atomic formulas, the validities of atomic formulas are preserved in the intuitionistic accessibility relation. This is the first requirement. The second requirement is the confluence condition on the interaction between these two conditions. Namely, if some word is intuitionistically accessible and then model accessible to this, then this should also model accessible to this. And this is the only affluence condition on the interaction between these two relations. Now, those conditions that I described are kind of related to guarantee that the validity of formulas are being preserved when you go up via intuitionistic accessibility relation. If these conditions are added, then you would have an intuitionistic crypto model as described. That's it. As much as we don't require any condition. At this point, no condition is required. They even could be inconsistent at this point. So the soundest result also could include in principle the inconsistent theories as well. But in practice, when we provide a previous model in completeness results, we actually provide these logics, these theories to be sound in this sense that all theorems that are being proved are also valid in that node. So they could not be inconsistent in practice when we provide um, the completeness proof, but it is not necessary even to be consistent here. So we don't have that property that you're telling. Unless as much as your paying attention to the set of formulas if it is gamma full. For instance, if you require that this probability model is gamma full, then if you restrict your attention to the gamma formula, then it would be satisfying the upward. Yeah, yeah, because we require to. Yeah, yeah, we will show this. The completeness also holds for these two logics as well. And well, one more attention here is that usually in the multi-models of intuitionistic model logic, one satisfies one requires this relation, this model relation to be transitive. But here we didn't require this. Even this condition is not required because of the closure under necessitation. You already have the transitivity, the validity of transitivity axiom. So you don't need transitivity. This is one of the places that you could replace some frame property with some inference rule condition. We replaced transitivity with closure under necessitation. We could do it the other way around, but no, we just kept with the minimal conditions on the frame properties as much as possible. Okay. Okay, we have these nice soundness theorems, which would be accompanied by completeness results as well. So we also have the completeness of IGL H1 for these logics and for these probability models, and IGL CA H sigma for these kind of probability models. But the problem is that for the completeness result, for instance, I will prove the completeness of this one here. This one is a bit troublesome. I cannot actually do this during a single whole session. It has lots of technical lemmas, but it is very standard way of constructing a canonical model by restricting to a finite set of formulas. It is not such a non-standard way of proving some new uh, by canonical model construction. But here, for IGLCA, for instance, you don't need even canonical model construction. You can just start with standard Kripke models that being constructed in the canonical model by construction of canonical model and just attaching theories as a subset of valid formulas to that node, and you're there. So let me describe how the completeness for this logic would work. Here exactly where I need these two characterizations. As I promised, that these two characterizations are being very helpful later on when we are talking about probability models. They are exactly used for the proof of the completeness part. Namely, let me show you that why the completeness part for this logic actually requires this characterization. Okay,
The thing is, this is required for computing.
for the completeness.
Okay.
For the soundness, we have seen that.
Yeah, the sound is very straightforward. Yes.
Soundness, actually, we have seen. The proof is as what I have written. Well,
Okay.
if you need details, you can
Yeah,
do it
yeah.
yourself, but it is more or less the same.
Okay.
It's very automated. What is the completeness of that? So the theorem that I now want to prove is the completeness of I D L C A H sigma is complete. I don't write the details, but complete for what? For probability models which are satisfying these conditions, namely this CA model, and they are SN full, and they are closed under necessity. So, so assume that I D L C A H sigma does not imply A. So the whole point of this system that I have written here, actually, I'll write it out, which actually axiomatized this system, was to serve as a system to enable us to calculate the nil approximation, right? So um, we can calculate the nil approximation inside boxes as much as we are inside boxes, and we can do it in an iterative way. So the nil algorithm that I described in the first session would become a very handy tool here. And with the presence of the axioms in H sigma, a set of axioms, you can do it inside boxes as much as you're working inside boxes, and do it in an iterative way. So every nested boxes could be replaced with its nil approximation, and well, we just annotate it as uh, bracket A. But the whole point is that this system is capable of proving that A is equivalent to bracket A. What is A bracket? A bracket is the formula resulted from A by replacing any formula which is inside some boxes with its nil approximation from B. And they are equivalent as much as you are working. No, to be more precise, we are actually not only doing the nil approximation, we take the box translation as well. It is still valid and valid action to be done via these set of axioms that we already have here. And that's it. So we take nil approximation and then the box translation, and this is the formula which would be this formula that I described here. And then uh, one could forget about this kind of annoying axioms. Just take IGLCA. Now IGLCA does not imply A. And you can make a finite Kripke model construction for the intuitionistic model logic of IGLCA. We have the soundness and completeness in a very standard way. So we have a Kripke model K such that, well, I don't write the details of the case, such that for some node W, we have the invalidity of the approximation of A, right? It is what we have by a standard argument of intuition, Kripke model of intuitionistic model logic. At this point, I should address some probability model out of this Kripke model. To describe this probability model, the probability model would be just Kripke model together with the logics, the theories actually, in which the TW is defined as just intuitionistic logic plus a set of formulas in S nil such that uh, P and W forces B. Pay extra attention to here that we are not in a circular uh, argument for definition of this probability model because the validity of the formula in a node only only requires the evaluation for atomics and the already defined the definiteness of the theories that are above that node. Which by recursion on the nodes, we know that this Kripke model is converse well founded, so we are allowed to do induction on the nodes, and from top to bottom, we define these theories one by one to arrive at this definition. And well, that's the definition of this probability model that is going to serve as the counter model for A. Let us see that why is a probability model of our interest. I will wipe this out.
Actually, so I think you can say so it's fine, but actually, where the language of the model coming from?
It is by canonical model construction. It is a very standard way of providing picture model. It's very easy to very standard, not easy, standard.
Okay, it's okay.
So you already have this result.
Okay, so you take you construct harmonic model for the and then okay, and then what you want want to extend this with yeah with probability. I mean, but also it's like well, I don't know because okay, so well, like usually we don't really use canonical model.
Yeah,
we usually find
your attention to some set of restricted set of formulas as a subset of well, some adequate sets would be.
no, I mean the difference. I mean there's two differences here.
Oh,
Like,
okay.
I mean, like what you when I think about adequate set, okay, yes, it's standard multivariate implication to make canonical effectively like you finite variant canonical model.
Right.
And second thing is, I mean, I just want to familiar how you do it for gel, but like for normal gel, you
Make it irreflexive.
because you want make relation reflexive.
Yeah, exactly. In the same way that it works for GL, here also you should do the same trick.
Right. Okay, that's just to make things. Who actually is familiar with canonical model construction for for general information. Good time. Yeah, no, I don't think people know.
Okay. I can explain in the next session a complete explanation, but maybe we can do some kind of group study. It is not meant to be a course. If it is meant, I can teach for a whole semester, and happily I would do that.
Okay.
But I guess for
Anyway.
a series of it is impossible to do.
Maybe you don't.
Yeah, I guess. That's why I say, well, even by skipping these amount of standard motion in this non-standard argument, actually, well, I am still a bit well, late for finishing this session. Let me get back to this. Okay, we have this probability model as described here. We want to see that why this probability model is actually um, uh, a probability model which satisfies those conditions that we required for the soundness part. You remember that which conditions we required for the soundness? We required the SN fullness. FL fullness is already satisfied here because we defined it in this way to be serving for SN fullness. So SN fullness is already there. It remains only to make sure that it satisfies the other extra condition, namely closure under kind of relations. Okay, if I show that for a moment, let us assume that we already proved that these theories are closed under AR sigma relations. Namely, if TW implies some A, some E, and E triangle F is implied by AR sigma, then TW also implies it. We already have this condition, this closure condition that we required for the soundness. So we have the soundness of this probability model for this system of IGLCAH sigma. And then if we assume that we already have this, I will prove this. For a moment, let us see that why it is needed, why it finishes up the proof. Because no, we have this P and W also does not forces the A. Why? Because actually this probability model and the standard Kripke model that we started with are coinciding as much as we are only having formulas in this set of formulas whenever they appear inside boxes. So given that the approximation of A only includes S-nil formulas inside boxes, this probability model coincides exactly with this Kripke model, as much as formulas are only having those kind of box formulas. Then we also have the invalidity of this formula in the probability model. And then uh, given that this probability model is model of this logic, and A is equivalent to its approximation in that logic, we could say that P and W also refute A and W. So we have a counter probability model and we are done. So it only remains to show that why this holds. The reason that this holds actually goes back to this characterization, where exactly it is needed. Assume that PW implies some E, and assume that E triangle F is derivable in this admissible rule system. Then, by definition, it means that in the intuitionistic logic, we have a finite subset of this set, namely, well, given that S nil is closed under conjunctions, you can just take a single formula in S nil. So there is some single formula phi in S nil such that phi implies E, right? If phi belongs to S nil. Okay. Now, given that E triangle F is in the AR sigma system, we can say that we also have E preserve F for S nil and IGLCA. Okay. Now, given that intuitionistic logic implies this implication, so IGLCA also implies this implication, and well, and IGLCA should also imply phi by our theorem first, by theorem one. Here we are actually using theorem one. That IGLCA also implies phi implies F, and then we are there because this also should be T W because phi belongs to T W. And IGLCA also belongs to T W and the other. So we have the closure of TW under pairs of formulas which are derivable in AR sigma. So we have the closure condition and we are. So we have a proved now. Yes, Yes, it is exactly intuitionistic logic in the extended language by model. At this point, no. I only used this fact for this characterization actually because I needed to use this characterization. I written this condition to write. Yeah, but in the next part we have seen that for any probability model in the soundness part, actually, I grabbed the attention. I would say it again. If you consider some probability model which is satisfying these basic properties that I mentioned, closure under necessitation and modus ponens, by induction on the set of words, you could say, you could prove that all the theories should include IGLCA. In the end, no, no. But well, in the definition they are not included. But afterward, we noticed that they they actually included. And no, this is the soundness and completeness for probability model. The soundness and completeness for these kind of probability models is way more difficult. We need some extra works. Maybe next session I don't pay attention to this and directly goes. I will go to dust reduction. It depends on what is more uh, wanted from the audiences. But my plan is to not go further for the proof of completeness of this system IGLH1 for these kind of probability models and directly use this result for the purpose of providing the reduction process. So such that I can arrive to describe in more details that how this kind of reduction would work. Actually, for that purpose, we need a third theory in between of these two theories. The reduction is not going to work directly from IGL H1 to this logic. Some intermediate level would be needed. I will describe next. Okay. I'm done with my presentation for this set.
Questions online?
Fine.
Yeah.